The new chapter for the syllabus is the chapter number 5, Introduction to Euclid's Geometry. What is geometry? We have come across this word many a times in the branch of mathematics. Geometry. Let's see the root cause of the introduction, geometry. Geometry in the branch of maths is divided into geo plus metry. So geo in Greek generally refers to earth, and metry in Greek refers to measure. So the Greek names for geo is earth and metry is measure. The measure of earth is what is called geometry. But why did the mathematicians during those times did give importance to measuring earth is the biggest question out here. So in order to solve this issue, or in order to understand the reason behind, let's try to take the history back into existence. Going back to history, during those times, many Greeks had different plots or the farms which the farmers have divided. So every land was divided into different farms and then connected with the farm of the other farmer. And this is the farm of the other farmer. So they had many irregular shapes through which the farmers had their farms. So with this irregular different plots of the farms which the farmers had as the agricultural land, it was very difficult to recognize the boundaries, because during those times the river Nile with heavy floods used to flush out the boundaries. Usually the farmers used to keep the boundaries out with some indication and the marks. But when the floods arise, or when the river Nile, which is besides, overflows and the water flushes in to the agricultural fields, then the whole boundaries used to vanish. Imagine the farms or the plots which are irregular in shape, which had their boundaries marked, have washed away. How do we recognize the boundaries? How do we recognize the plots? So the farmers during those times had various issues regarding the exact geometrical structure of their respective farms. So this problem has been a serious issue during those times in historical facts. So this is the reason why many mathematicians have come into expecting some mathematical solution for this problem, and hence arised the topic geometry, the measure of earth, the measure of the lands, the measure of the plots. So once the plots are lost out through the washed, flooded out waters, then reconstructing the boundaries was done through the geometrical measurements. So the geometrical measurements were strictly the inventions of the topic of geometry dedicated to all the past mathematicians. Geometry, geo for earth, metry for measure. The study of earth or the measure of earth is called geometry, the topic which we're going to learn for today's session. Now, before we enter into the topic of geometry, it is very essential to investigate the historical facts which make us realize that different civilizations have approached in different manners for geometrical concepts. The Egyptians had their own way of measuring the volumes and the areas of various geometrical structures in their own manner. The Babylonians had their own way. The Chinese had their own way of measuring. The Indians had their own way. So every civilization has approached in a different manner, but ultimately the process coming out to be unique. So let's see all the civilizations combined to understand the geometrical concept of identifying the areas or the volumes of various different geometrical structures like the cone, the cylinder, the sphere, the pyramid, etc. Geometrical structures and their mathematical properties to be continued. Now let's see the Indian civilization which had its contribution in the world of understanding geometry and the geometrical structures. As in ancient days, the Harappan and Mohenjo-daro the Harappan and Mohenjo-daro civilization had been excavated through various investigations. It has been excavated that these civilizations were highly civilized or highly developed in the society during those times, and this was strictly dedicated to the geometry behind the civilization. So let's see how geometry played a vital role in uplifting the civilization into a higher or the highest society, in the respect of the highest society. In Mohenjo-daro, it was known that most of the roads were parallel to each other and they were exactly perpendicular. Even the concept of perpendicular or 90 degrees was used in construction of roads. So they had the roads which were well mannered and exactly constructed through the geometrical measurements was assumed. Even the houses which were constructed and the rooms which were built inside the house were said to be totally based on geometrical concept, as clearly evident through the historical facts behind the civilization explored through the excavation. So all these things, even the drainage system, the Harappan and Mohenjo-daro civilization is assumed to have the underground drainage system, which was not existing in any other different places there during those times. So the drainage system in the undergrounds was a startled investigation or a startled exploration from historical facts, which has been existing from those times. So this civilization was very much witnessed with geometrical importance and the constructions through the geometrical significance. The Sulbasutras and many of the Vedic ancient scriptures, the manuscripts, are all clearly evident. Even the temples at which many symbols clearly indicate the importance of geometry, especially the Atharva Veda, which has the Sri Yantra, is interwoven with 9 isosceles triangles, which then lead to 42 subsidiary triangles. So many historical facts are witnessed with geometry and its importance in real life. History behind mathematics. History behind Indian mathematics. Before we enter into the introduction of geometry in its mathematical background, let's see how different mathematicians have understood geometry before they could apply geometry into the mathematics or into the real life. So Euclid's understanding of geometry. Let's see how Euclid's have understood geometry in his period of time. Euclid's geometry. So Euclid's understanding of geometry is what we're going to discuss in today's session. In Euclid's understanding of geometry, we need to understand some basic concepts before we understand the geometry itself. So let's try to understand how Euclid has come into different basic properties before he could apply geometry in various real-life situations. For this, let me take an example of a cube for you to understand how Euclid's geometry can be applied or has been applied through each of the developed contents. Imagine I have a cube or a die. We all know that a die has 6 faces. So I take the example of a die in which each face of the die is called a surface. So Euclid has taken each face to be a surface, and each surface is nowhere related to the other surface. That means when I take this in this region, the other surface lies entirely in other space. So according to Euclid's geometry, every surface is in its own space, the other surface being in the other space. So each of the 6 surfaces will be in each of the different regions, is how we understand Euclid's geometry. And according to Euclid's geometry, every surface with the other surface is separated by a line or a curve. In this case, this surface being separated from this surface by this line, as can be clearly seen. So the surface 1 and the surface 2 are separated by a line or a curve. So in this case, a line separates the 2 surfaces. And further, Euclid's geometry understands that all the lines meet at a point. So here, this line, and the other line all meet at a unique point. So according to Euclid's geometry, 2 surfaces, any site which is in its own space is a surface of the die, and the 2 surfaces are in their own respective spaces but not in the same space, and both the surfaces are separated by a line or by a curve, and all the curves of the lines meet at one point, is how we understand a 3-dimensional or an object like a die, which is separated by first with a surface and then with a line and a point. All the surfaces make the line and all the lines make the point, is how we understand, with each of the surface making the line and each of the lines making the point, is how Euclid has come through the introduction of geometry. So all surfaces make a line or a curve. All lines or curves make a point, is how we understand. And we also understand that it is the surface which makes the line, and it is the lines which make the point. And this is how the transaction happens: surface to line and line to point. And surface is referred with 3-dimension and this refers to 2-dimension, and this refers to unique dimension, is how we understand. So before we understand this, let's try to understand on how the dimension is understood through the solid structure. Euclid's geometry connected with a rolling die. Now let's understand Euclid's geometry through a three-dimensional object, just like a dice. So let's take an object and understand the concept more stronger on how Euclid could understand geometry during his times. So as we have seen a dice, I assume this to be a three-dimensional dice in which I have 6 faces: face 1, phase 2, phase 3, phase 4, and phase 5, and phase 6. So in this, each of the face is called a surface according to Euclid's geometry, as I refer with the surface. Now as I see that every surface is in its own space, that means this surface cannot be in this space, or this surface cannot be in this space. Each surface is in its own space, is how we understand the surface. So every surface is separated by spaces. And also, as I see the two surfaces, I can see that this surface and this surface is joined by a line or a curve, depends on the structure. Now every surface, say for example this and this, is separated by a line. This surface with this surface is separated by a line. So therefore, the two surfaces are separated by a line. All surfaces make a line. Now let's see how the lines make the point, or how the curves make the point. As I see here, the line 1 made by these two surfaces, and the line 2 made by these two, and the line 3 made by this and this surface, all the three lines, line 1, line 2, and line 3, all meet at this point. So this is the point where the three lines meet. So this point is made, indirectly is assumed to have been made by the lines of the solid structure. Say for example, I take this point which is made by this line, and this line. Therefore, the lines in the object make the point, is how we understand. So basically, the transaction goes that a solid, or the object itself, in this case being a box, makes the surface. The box is the initial making which makes each of the 6 surfaces. The solid makes the surface, and the surfaces make the lines or the curves, and the curves or the lines make the point. So the solid structure defines the surface, surfaces define the lines define the points, is how we understand the transaction series in the Euclid's understanding of geometry. Also, let's make the most important note in this case, that a solid is referred to as the three-dimensional structure. A surface is referred to two-dimensional structure, and a line is referred to a one-dimensional structure. A point is referred to a zero-dimensional or no-dimensional structure. The dimension of a solid is 3D, and as it goes here, it reduces by 1 unit, and as it goes here, it reduces by 1 unit, and as it goes here, it reduces by 1 unit. So the dimension of the specimen gets reduced by 1 unit as it gets reduced to a point. Solid 3-dimensional reduces to surface, which is 2, the line, which is 1, and then to the point, which is of 0 dimension or no dimension, is how we understand the concept of a solid structure to reducing to a point in Euclid's understanding of geometry. To be continued, we have the Euclid's understanding of geometry, which had the further properties which Euclid has referred in one of the most famous book called Elements. In the book 1 of Elements, there are totally 23 important points which are noted down by Euclid and his contribution to mathematics. Some of them are as follows, which are very important to understand as the basics before we enter into the concept of geometry. And the first property is that a point has no part. As you take a pen, it has a part because this is the piece of the pen. This is the piece of the marker pen. It has a part. This is the piece of the cap which has its own part. Is how we understand the content which has a part, but a point which I take, in this case, a point has no part. So my first property says a point has no part. It is itself a dot, represented by a dot. It doesn't have any dimension, and therefore a point has a zero dimension. And this is the reason why we say a point has zero dimension, no dimensions at all. The first Euclid's exploration is that a point has no part. Secondly, Euclid has come out with a line is a breadthless length. What do we mean by breadthless length? For example, I take a rectangle. This is the length and this is the breadth. Now, this cannot be a line. It is a rectangle, which is a surface. So this becomes a line when the breadth is 0. That is, it is breadthless. Mathematically, b is 0. So this length converges, and a line is a length which does not have breadth. This is a line because it has breadthless length. It has L, but it does not have B. This has L and this has B, so it is not a line. This is a line. According to Euclid, a line is a breadthless length. Now, the third exploration of Euclid in reference to geometry is that a line has the two ends of a line are points. This has been the great invention during those times where a line, imagine I take a line L, the end points of the line are points. Say I take P and Q. Euclid says the end points the ends of a line are points, is how Euclid has come to the conclusion. The ends of a line are points. In this case, being P and Q are the endpoints of the line. Euclid's geometry refers to a line whose endpoints are the points, always, for any line taken in the branch of mathematics. A line whose endpoints P and Q are points. The fourth point which Euclid has referred is about a straight line, defining a straight line. A straight line is the one which is evenly distributed with all the points on itself. The line which we are learning for today was one of the greatest and the efforted invention during those times. A straight line, according to Euclid, is defined to be the one which is evenly distributed with all the points on itself. That is, if I take the points, they must evenly distribute so that the line must exactly be passing through those points, is how I define the line. If the points are unevenly distributed, then the line cannot be passing through that. According to Euclid, this does not define a line, but this defines a line, because the one which is evenly distributed with all the points on itself is a line. Which is unevenly distributed with few of the points not on the line cannot be a line, cannot be a straight line, according to Euclid's geometry, is how we understand the property number 4. A straight line is the one which is evenly distributed with all the points on itself. Now, the fifth asserted principle of Euclid in its book of elements is that a surface is the one which has length and breadth only. So, this refers to the point number 5, which says a surface is that which has length and breadth only. A surface is that which has length and breadth only. It doesn't have anything else other than length and breadth. For example, I take a rectangle. Rectangle is a surface which has length and breadth, but it does not have anything else other than length and breadth. So this is a surface. This is also a surface. This is a surface. This is a surface because it has length and breadth, is how we understand the surface, each surface of this box. Surface 1, surface 2, surface 3, surface 4, surface 5, and surface 6. 6 surfaces making a box. A surface which has length and breadth. A line which has length but does not have breadth. A line is a breadthless length, is how we understand the difference between the surface and the line. And the last property which we are going to study in understanding of Euclid's geometry is the 6th property, which says about the plane surface. According to Euclid, a plane surface is the surface which is evenly distributed and with straight lines taken on that to be itself. So, with the straight lines on itself is how we understand the plane surface. For example, I take this. This clearly is a plane surface because it is plane in our understanding. But according to Euclid, mathematically, a plane surface is the surface which is evenly distributed with no ups and downs, but plain and flat, and with straight lines on itself. If I take any two straight lines, they will be on the plane, but they will not move away from. All the complete straight line must lie on the plane surface. If it was a bulged surface, for example, I take I have a surface which is bulged out here, then a straight line does not completely lie here. It just cannot move. If I take a straight line, it moves outside of. As clearly seen, tangentially it moves out, but this straight line is not on itself. Since the straight line drawn on the surface of this particular diagram, the straight line drawn on the surface, on this surface, does not entirely lie on the surface. Therefore, according to Euclid, mathematically, this is not a plane surface. Therefore, this is not a plane surface. That's how we understand the concept. Plane surface is a surface which is flat, and mathematically any straight line lying on the surface must entirely lie on itself. Is how we understand the plane surface according to Euclid's geometry. So these are the different properties through which Euclid has come out with his investigations and his research, which has been reflected in the Book of Elements. Euclid and his geometry contributed. Now that we have discussed about Euclid's contribution to understanding the geometry in his own mathematical understanding in historical facts, let's see the most important concept as contributed by Euclid, called Euclid's postulates. There are 5 postulates which are recognized in the branch of mathematics and are found to be very helpful in mathematical understanding. So let's see the 5 Euclid's postulates, the contribution of Euclid in geometry. Euclid's postulates. Each postulate has its own understanding, which helps us in understanding various geometrical properties involved in real life situations. So coming to Euclid's postulates is the topic of the session. To start with, postulate number 1. Postulate 1. So what was Euclid's postulate number 1? Postulate number 1 states that if I take any 2 distinct points in the plane, randomly any 2 distinct points taken in the plane, then Euclid's postulate number 1 says that there's only one and unique line which passes through those 2 points. You cannot have more than one line which passes through. So here the postulate number 1 says, given the 2 distinct points one and only one line can be drawn passing through them, that is, passing through the 2 distinct points. So postulate number 1 clearly says, given the 2 distinct points, one and only one line can be drawn passing through them. This is one of the most important invention during those times in history. We are applying the concepts in the modern times, but everything has originated from the Euclid's postulates. his contribution to geometry. So let's see the statement in brief, the postulate number 1 in brief. The postulate number 1 says, given the two distinct points. So let me take the 2 points which are distinct in the sense they are not same from each other. They are different from each other. So given that there are 2 points which are different from each other, then Euclid's postulate number 1 says that there is only one line which can pass through them. It's very clear that when we take the ruler and try to draw a line joining the 2 points, obviously you have only one line which can pass through them. You cannot investigate on trying to draw another line passing through the 2 points. Is how Euclid has contributed through postulate number 1. Given the 2 distinct points A and B, there's only one and unique line which can pass through them. So according to postulate number 1, this is called the unique line through A and B. So here the line which I draw through A and B is the unique line. That is, note there cannot be any other line which can be drawn there cannot be any other line which can be drawn through A and B. This is the only line which can be drawn through A and B, is how I understand the postulate number 1. Given 2 distinct points, there's only one and only one line, a unique line which can be drawn through A and B. No, more than one line is not possible according to Euclid's postulate number 1. Euclid and his postulate number 1 contributed to the mathematical society. Now that we have learnt about postulate number 1 as contributed by Euclid, let's now see what postulate number 2 states in its own definition. Postulate number 2. Now before we get into the postulate number 2, we all know what a line segment is. In the modern times, we have been discussing about a line segment, what Euclid has called during his times as a terminated line. So as we take, let's see the definition and then get into understanding the concept by taking an example situation. A terminated line can be produced indefinitely. So here the postulate number 2 says a terminated line can be produced indefinitely. So what does this mean? A terminated line is the term which in modern times is referred as the line segment. We all know what a line segment is. The line which has ends towards the right and the left. Suppose I take a line segment AB. So here is my line segment. So my line segment is connected by the points A and B. So the terminated line is the line which ends on either side, is what Euclid has defined in his own terms. So in terms of line segment, the line which ends on both sides can also be produced according to Euclid. His postulate number 2 says that a line which ends at 2 points can be extended on either side and also can be extended onto this side, so that this line can be a straight line which can indefinitely be extended on the right and the left. So this line goes till plus infinity on the right and minus infinity on the left, is what we have learnt in the real number line. So a terminated line can be produced indefinitely on either side of its terminated points A and B, so that we get an infinite line, or it can be produced indefinitely, is what is postulate number 2 defined as Euclid's contribution to mathematical society using the postulate number 2. A terminated line can be produced indefinitely. Now let's enter into postulate number 3. The postulate number 1, postulate number 2, and now to come with postulate number 3. According to Euclid, his contribution to postulate number 3 was more focused on a circle. As we have seen, a circle with center and radius. So Euclid has investigated on the circle with its center and radius, and hence has come out with postulate number 3. Postulate number 3, as derived by Euclid, dedicated to the circles, the radius and center. So let's see what the postulate number 3 states. A circle can be drawn with any center and radius. This is what the postulate number 3 states. A circle can be drawn with any center and radius. So this investigation, clearly as evident on recognizing the different circles, was what has come out with the outcome of postulate number 3 by Euclid. As we can see, let's start with a circle. We know that when you take a fixed point and take a compass and just rotate it, I get a sort of a circle out here with the center here. Let me take the compass with a more bigger region, and then I get the circle. Let me now take a very small region of the compass and then try to rotate. I get the circle. So here I have circle 1, circle 2, and circle 3, which have their respective radii. So each of the circles have their own radii in this case. So Euclid says that any circle can be drawn provided we have the fixed distance between what we derive the circle as. So according to Euclid, a circle can be drawn with any center and radius. This is with a center and a radius, and this is with another center and another radii, and this is with different center and radii. All three are circles. All these three are circles. So any circle, however big or however small, can be drawn with fixed center and radius, is what the postulate number 3 states according to Euclid's contribution to mathematical society. Next comes postulate number 4. Now Euclid is known also for recognizing or investigating many mathematical properties in right angle triangles. Just like Pythagoras has been investigating, Euclid has also contributed a lot on the right angles. The student of Thales, Euclid, has come out with his own contribution to the mathematical society. So let's see what the postulate number 4 contributes through the right angles. So the postulate number 4 says that all right angles are equal to one another. This might look very silly in the modern times, but it's very important that during those times where mathematics was very limited to its own knowledge was a very great invention, as with the postulate number 4 by Euclid. This is to be taken into mind very seriously. So postulate 4 says all right angles are equal to one another. Let's see how we can justify the statement. Let me take a right angle which is measured out here between the lines L2 and L1. Let me take another situation where I have a right angle, that is I have here between the sides BC and AC. Let me take one more situation where I have a right angle. For example, I have a circle or I have one more circle property which says angle in a semicircle is 90 degrees. So in this case, I have 4 cases of right angles, where in this case I have the line L1 which is exactly at 90 degrees. Usually 90 degrees is denoted by this symbol square. So this represents angle 90, is how I understand the 90 degrees concept. Similarly, I have triangle ABC in which angle C is 90 degrees through the sides BC and AC. Next, I have a circle in which at this point P, the tangent is set to make 90 degrees with the radius. This is the radius of the circle and this is the tangent, and at the point the tangent is set to make 90 degrees with the radius of the circle. Similarly, I take a circle which passes through the center of the circle, then this is called angle in a semicircle which is 90 degrees. So this is how I justify the property. In a semicircle, angle is 90 degrees. So in each case we have 90 degrees, which is different in different situations. But according to Euclid's postulate number 4, Euclid says all right angles are equal to one another. The 90 degrees here must be equal to the right angle which is 90 degrees here, must be equal to the right angle which is equal, or the 90 degrees in this case. All these 4 right angles are said to be equal in their own respective manner. So according to Euclid's postulate number 4, all right angles must be equal to the other, however different they are in their own geometrical situation. They are right angles, they must be equal. Now let's see the postulate number 5, the last postulate in Euclid's contribution. Postulate number 5. Now coming to the postulate number 5, before we discuss its complete definition, let me tell that all the 5 postulates are dedicated to Euclid, but the first 4 postulates are very simple to understand because they are self-evident. We can analyze obviously when I say all right angles are equal to one another, that means 90 degrees, it will be same anyway. So they are not that much focused on. But the fifth postulate, which is very complex, is how Euclid has contributed to developing the geometry as ages pass by. So let's see the postulate number 5 contributed to geometry. According to Euclid, if there are two lines out here, and then if there's another line which cuts this with interior angles being, say, this is x and this is y, then if x plus y is less than 180 degrees, according to Euclid, this was referred as two right angles. So according to Euclid, if some of these two angles formed by the line, so this is P and Q, if this is the line PQ which makes the angles x and y in the interior angles on same side, say for example, if I take on the left side of the line PQ, the interior angles are x and y and the exterior angles are the one which are outside. So when I take the interior angles x and y, the condition is if x plus y is less than 180, then the postulate number 5 says the line PQ cuts the other two lines L1 and L2, and obviously in this case here they cut at P and Q, is how I understand the postulate number 5 as connected with intersecting lines. So with the condition that the two interior angles on the same side of the line being less than two right angles, that is one right angle is 90, so two right angles make 180 degrees. So we call 180 degrees as two right angles. Then if the sum of interior angles is less than 180 degrees, then the line PQ, as clearly can be seen here, cuts the other two lines L1 and L2, obviously at P and at Q, is how we understand the postulate number 5 as contributed in the mathematical society by the great mathematician Euclid. Today's session is about postulates. The Euclid's postulates is what we are going to define or discuss more of in today's session. So let's see what are postulates. So the contribution of Euclid's postulates, but before that we will try to see what exactly the word postulate means in mathematical understanding. Before we discuss in brief about Euclid's postulates, the 5 postulates as contributed by Euclid in the mathematical society, let's define what a postulate is. What is a postulate? The term, which looks very complex in mathematics, has got a very wide definition and which plays a very important role in the benchmark of geometry. Postulate means making a statement on observed phenomenon. Postulate generally means making a statement on observed phenomenon. Its proof, its truth and validity is then checked later on. So here I have these two important things which are interlinked and defines a postulate. It's very important to understand a postulate in mathematics before we get into understanding geometry. So in mathematics, it is assumed that there are many proofs or theorems or many axioms or many postulates which have been invented or discovered by the past mathematicians. So here the postulate is defined to be making a statement on observed phenomenon. So generally when I make a postulate, it is about that I don't prove it, but I just make a statement on observed phenomenon. Just like I point out in the student, if a student is consistently talking in the class, then I rate him as a talkative person. This is the statement which I make on the observed phenomenon during the class session. In the similar manner, when I observe certain mathematical properties, it to be true in all times, then I say this will be true forever, and hence it's a postulate. To continue with this, its truth and validity also plays a vital role. When I say that I make a statement, I'm not going to make it unjustified. When I say the student is talkative, I'm not just cursing on him, or I'm just not taking revenge on the student. It is because his behavior in the class is talkative, I point out saying, you are talkative. So similarly, when I justify on whether the statement which I'm making is correct or wrong, I try to justify it on later on by applying that into the situation. Let's take an example problem to understand the postulate more better. Imagine I have 2 points which are distinct and very far away. Now I take a ruler and I try to draw a line passing through them. So when I take the ruler and just try to draw a line, I just see that there's only one line which can be drawn. So for these two distinct points as taken on the plane, let's see how we can connect this with a postulate. Imagine the two distinct points A and point B. Now let me just investigate on a property which can be invented or derived from this investigation of two distinct points A and B. Now for these two distinct points, I would like to see how many number of lines I can draw. So I try to make an attempt in drawing this line which doesn't pass through the points. Then I make an attempt to draw a line passing through this and attempting to make this line pass through the other one. This also does not pass through the other line. So with this investigations, I wonder to see, is there any line which can pass through the 2 points, and how many such lines can be passed through that 2 points. So as I see here, I come across a line which is set to pass through A and B. Now out of the different lines I have taken, I recognize that there is only one line which can pass through these 2 points. Or out of all the different possibilities of different lines I take, I see that there's only one line which passes through A and B. So I make a statement through my observed phenomenon which says that there's only one line which can be made to pass through two distinct points. Then that makes my statement, which is on the observed phenomenon. Now comes its truth and validity, which is checked later on. So I take the plane, I plot the points, the two distinct points, and then try to make different lines possible. Then I check through the validity that yes, there's only one line which can pass through the 2 points, and hence it is called a postulate. Similarly, I take a point and I want to see how many lines are possible to be drawn from this point. So I investigate with 1, 2, 3, 4, 5, 6, etc. So different lines pass through the point. So I make the statement that there are infinitely many lines which pass through that point. So my postulate is about making a statement on observed phenomenon is that infinitely many lines pass through the point on observed phenomenon. And I check through the truth and validity. I draw the different lines and I see that there are infinitely many lines which pass through the point. Is how the postulate comes. Truth and validity check out. And only if it is true, we call this as a postulate. If my truth and validity, which is checked later on, does not prove the made statement, then it cannot be a postulate. We cannot call that a postulate. Postulate is a statement made on observed phenomenon. Its truth and validity checked later on. If the truth comes out to be universally true, then the statement is a postulate. It must be called a postulate. Euclid's postulates to be followed with. Euclid's postulates. Now that we have seen the 5 different postulates in Euclid's contribution to mathematical society, now comes what are the uses of these postulates? Where do we use them? What are the significances of the 5 postulates as we have learned in the previous session? Is the biggest question which arises next. So Euclid's contribution is about his postulates which are applied in different axioms, theorems, or various properties in mathematics. So let's see few of the properties in mathematics where Euclid's postulates are exclusively used in deriving those properties. So here comes the topic applications of Euclid's postulates. So let's see the different applications of Euclid's postulates in brief. As we have seen the different 5 postulates, let me come with this property. Say I have a line segment which is divided at A, at B, and C divides the line AB. So in this case, I clearly see that the distance AC and the distance BC when added gives me the distance AB. Therefore, the property says the distance AB, the distance AC plus the distance CB is equals the distance AB. Is how I derive using the Euclid's postulates. The postulate which says between 2 distinct points there is only one line which can be drawn, and therefore I have only one line which passes through A and C, which are the distinct points, and there is only one unique line which passes through C and B, which is unique, and therefore this will be a complete same line which passes through all the 3 points. You cannot draw more than one line passing through A, C and B taken in pairs as distinct points, AC and CB. So this postulate number 1, as we have discussed in Euclid's postulates, we have a property which says the sum of 2 sides is the sum of the longer side. That is, AC plus CB will be equal to AB, is how the property gets derived using the Euclid's postulates. Significance of Euclid's properties or Euclid's postulates in the branch of mathematics. Property AB plus BC will always be equal to AC. if the 3 points A, B and C are on the same line as given here. A, B and C are on the same unique line. Cut. Let's see one more mathematical property which has used Euclid's postulates in its own derivation. So as we say, Euclid has used his postulates to prove that an equilateral triangle is a triangle which has all three sides equal, as we know. An equilateral triangle can be constructed or derived from any line segment. Is how we understand the postulate. An equilateral triangle can be constructed or derived from any line segment. So let's see how we use the postulates in this. So Euclid has come out with taking a fixed line segment AB with terminated line, as he used to call during his times. He has taken a terminated line AB and then tried to construct an equilateral triangle using this dimension AB. Therefore, he has come with the measurement and then used the circle property to construct an equilateral triangle from a line segment. The circle property, as he has defined that any circle with any radius can be formed. A circle can be formed simply by taking different radii and different centers. Therefore, he has taken a circle fixed with A and then cutting an arc. So he has made a circle passing this way. And then from this B as the center and AB as the radius, he has cut another circle out here. So there are two circles which are formed out here, cut. Now this point of intersection was taken as a third coordinate C. The two circles derived cut at one point of intersection, which is called the point C. Now as you join this and as we join this, we get an equilateral triangle. An equilateral triangle which has all the three sides equal is how Euclid has come out with any circle can be drawn with center and radius. So he derived different circles within the line segment and then the point of intersection was joined to form triangle ABC is constructed equilateral triangle because AB equals BC equals AC. So triangle ABC is constructed equilateral triangle with all three sides equal. So in this manner, any line segment can be taken to be just intercepted and I get an equilateral triangle. I take another line segment which is smaller in size. I use the same concept of cutting the arcs and then I join to get an equilateral triangle. Or I take a very big line segment, cut an arc with the respective length of the line segment as radius and the point where the two circles intersect, I join the other two segments and I get an equilateral triangle. An equilateral triangle can be constructed from any line segment is how we understand the postulates of Euclid applied in real life situations, constructing an equilateral triangle from a fixed line segment out here. Now let's see the theorem. Let's see how Euclid has proved a theorem using the 5 postulates which he has used in his contributed life, which he has invented in his contributed life. So let's see how the postulates have been useful in exclusively proving a new property through the contradiction. So let's see the property. To start with, Euclid's postulates helpful in deriving a theorem. So let's see how a theorem is derived using Euclid's postulates exclusively. The theorem says two distinct lines cannot have more than one point in common. So the theorem here says when I take two distinct lines, those two distinct lines cannot have more than one point in common. That is, the theorem says if I take two distinct lines which are not same, then when they are extended, obviously they have to meet at one point. So here, when these lines AB and CD are extended, then these lines meet at one point. They have one point in common, or they have one point of intersection. They must intersect, provided those two lines are not parallel to each other. So two distinct lines cannot have more than one point in common is how I understand the two lines intersecting. There should be only one point of intersection possible. So let's see how this theorem has been proved exclusively using the postulates. So the proof is by contradiction. Like given the statement, I take the contradiction of the statement and then prove that the result of that contradictory statement is not true using the proof. So now it is given that the two distinct lines cannot have more than one point in common. I take this to be line 1 and this to be line 2, and I assume that let the two lines which are distinct have more than one point in common. So cannot is now contradicted to be can. Let's contradict the statement that is, let the lines L1 and L2 have more than, or I can say have more than one point. That is, 2 points, 2 points in common. That is, the two lines are said to be intersecting at P and Q. Therefore, let L1 and L2 intersect at say at P and Q. Let L1 and L2 intersect at P and Q. Now here comes the concept of proving the theorem. Now that we have assumed that the lines L1 and L2 intersect at P and Q, therefore, but this is not true. Why do you think that this is not true? Because we have already seen in the postulate that there's only one line which passes through the 2 points. Now here I have 2 points through which it is assumed that there are 2 lines which are passing through L1 and L2. So here in this statement it is assumed that there are lines L1 and L2 which pass through P and Q, which is not possible, or it contradicts the statement, the postulate number 1. The unique line, there's only one line, one and only one line which passes through 2 distinct points. But here the distinct points P and Q, but there are 2 lines passing through the same point. So this contradicts postulate 1. Therefore, our assumption is wrong. What is our assumption? Our assumption that the lines L1 and L2 have more than one point in common is true, is false. So our assumption is wrong, implies the original statement is correct. So this kind of proofs are called proofs by contradiction, where I take the contradiction of the given statement. The distinct lines cannot have more than one point in common. Let's take the statement 2 distinct lines have more than one point in common and then prove by contradiction. So contradicting the statement L1 and L2 have more than one point in common. Say I have the lines which are intersecting at 2 points, or they have 2 points in common. So we have L1 and L2 intersecting at P and Q, say for example. But this is not true, because a line, there's only one and only one line which passes through the distinct points P and Q, but we have 2 lines which are passing through P and Q, and contradicts postulate number 1 as discussed in the previous session. Therefore, our assumption is wrong. Therefore, the original statement is true. The original statement is true. The original statement which says 2 distinct lines cannot have more than one point in common. If the 2 lines which are distinct at the most can have one point in common, but not more than that. You cannot have 2 points of intersections for this lines intersecting. As we have already seen in the linear polynomial, the 2 linear polynomials intersect at only one point. This is how we connect the learned concepts in mathematics to Euclid's postulate and Euclid's contributed theorem. Theorem applied through postulates and proved mathematically.